Hi. So thanks, Greg, for the introduction. And I will speak about the joint work with Dana Moshkovitz. Okay, so lately there is enthusiasm about machine learning because of its great empirical success. And the reason that there is such a great empirical success is because we have a lot of data. And we can design learning algorithms that can be viewed as magician. It seems like they can do everything, and they can answer many questions. For example, to predict if someone will have cancer or not, or to drive in autonomously vehicles. And it seems like the sky's the limit, and everything is possible. But actually, this talk is about the limitation, about what learning algorithms cannot do. So what we do is consider some limitation of the learning algorithm and prove that learning algorithms cannot perform under this constraint. So the constraint that we are considering is bounded space. So I want to motivate you on why bounded space is so important. So first, this is a natural mathematical question. We considered learning algorithms that are efficient in time. So the natural step is to consider learning algorithms that are efficient with space. So I think that for this audience, I can stop. But still, I will give you some more motivations. So as I said earlier, we are in the middle of the big data era. We cannot expect our learning algorithms to remember everything that, this data. Another reason is that neural networks, another buzzword, has a lot of success. And it's a way to do machine learning that is very successful. But this can also be viewed as a bounded space learning. And it's interesting to see what this very successful algorithms cannot do. Another motivation is that the nervous system, the biological neural networks, they also perform bounded space algorithm according to the biologically plausible assumption in the neuroscience language, which basically states a few constraints that any model of the nervous system must fulfill in order to be considered a good model. And this set of constraints imply that the computation must be with the bounded memory. OK, so now after you're very motivated, let's define a few notions. So first, the famous PAC learning definition of variant. It's a way to say if some hypothesis class is learnable. So hypothesis class, a set of functions from some set of examples to 0, 1, are learnable if the following holds. If for any hypothesis in the class and for any distribution over the examples, so for each time steps, our learning algorithm gets some input, and then another input, and so on. And at the end, its goal is to return an hypothesis that is very close to the correct one. So this is the basic definition of learning. And what is bounded space learning? It's very simple, but no. The learner can have only B bits of memory. So assume that we have all the 0, 1 to the B memory states that the algorithm can be in. And now, at the beginning, let's say it's in the first memory states of all 0. And now, when the learner gets an input x1 and label age x1, it changes the memory state in some way, and then the example is disappeared. And then it gets another example, and the memory changes again, and so on and so on. At the end, it's supposed to say what is the correct hypothesis. So this is bounded space learning. OK, So what we are interested in is to prove lower bounds, which means that we can take whatever D and age that we like. We are taking age that is uniformly random from the hypothesis class and D that is uniform distribution. So this is even harder because we are saying even if the learner knows that D is the uniform distribution, it knows exactly how age is chosen, the underlying hypothesis is chosen, still it's hard to learn. Okay, so this is our setting, and let's just map everything we know on one table. So this table on the x-axis is the number of memory bits the algorithm uses, and the y-axis is the number of examples, and each algorithm is going to be a point in this table. So one algorithm that we can look at is an algorithm that just tests if each hypothesis is the correct one or close to being the correct one. So notice that the number of memory bits is very small. It's only log 8. Just remember the current index of the hypothesis. This is the smallest, in general, number of bits that we can hope for. But the number of examples that this algorithm uses, it's a lot. Because in the worst case, it has to check all the hypotheses. So this is one algorithm. So as I said, this is the best possible. So we cannot expect to have an algorithm with less than log age. So red denotes impossible, and green denotes possible. If we have more memory bits, it's great. Another algorithm is the one that simply saves in memory all the examples that it's seen so far. So the number of examples from the fundamental theorem of statistical learning, for example, is log age examples. And the number of memory bits is quite high, because this algorithm needs to save in memory all the examples it's in, so it's about log age times log x. Okay, so we must use at least log age, so this is also impossible. And if we use more examples, it's possible. So when you look on this table, you immediately ask, what's going on in here? Is everything red, green? What's going on? So Archimir asked me this question 3 years ago. He asked me, can you prove some lower bound for some class? And then a few years ago, Greg and other people from Stanford asked this question more publicly, and they left as an open question to prove limits of space-bounded learning for one specific class. For the class of parities that is known to be very hard, they assumed that they claimed that this should be also hard to learn with bounded memory, and they were right, because Ran Raz proved that this class of parities is indeed very hard. He proved like the best lower bound we can hope for, but for this class. And later, we proved also a lower bound, but for much general in the sense that most classes cannot be learned. But our bound wasn't as strong as Ran's. And later in this work and Ran, we were able to prove a very strong lower bound. And the funny thing is that we both used pseudo-random notions to prove a lower bound, but we used the combinatorial one, and he used the algebraic notion. And later, Avishai and Greg proved a much stronger bound than that. Okay, so now I want to tell you how we proved this stronger notion. Okay, so let's think about the main component, the main term, the probability of h given m. And when I'm writing this term, I mean what is the probability that the correct hypothesis, the underlying hypothesis h, given the algorithm reached at some time point to memory m. This is the main distribution that we are considering. So when we fix a learner and we said that the underlying hypothesis is uniformly at random, how this distribution, the probability of H given M, changes over time. So when t equal to 0, when we haven't seen any example at all, how this distribution is going to look like. So when we haven't seen any example at all, each hypothesis can be the correct one. So this distribution is the uniform one. And what's going on at the end? What's going on when the learner finished learning and he knows what is the correct hypothesis with high probability? So in this case, this distribution is going to be almost like delta function. Because for the time step, the last time step, the memory state, most of the memory states know what is the correct hypothesis. So it's going to be really close to 1 for the correct hypothesis. So what we said in our low certainty framework that we presented at COLT, we said that at the beginning, this distribution is random. At the end, it's really not random. So maybe we can prove that there is some pseudo-random property that only slowly changing over time. And this is why many examples are needed. At our previous work, we used the simpler notion of extractor-like definition. But this was very weak, and we were able to get to not such a good results. But what we did now is to strengthen this definition and define a new notion of pseudo-randomness. The entropy samplers that I will present in this talk, I will show it at the last slide. And this is the main thing. And this, hopefully, can be of independent interest in other places. And OK, so the most difficult part is indeed proving that this entropy sampler changes only slightly at each time step. This is the difficult part. OK, so now I want to define entropy sampler. And as I said, this is going to be at the end. And now I need some definitions. First, I need to define some definitions in order to formally define the entropy sampler. So let's begin. So I will start with just define multiplicative error sampler, which is known. So we want to prove that this distribution is pseudo-random. So notice that if we have some distribution over the memories, then this defines a distribution over the hypotheses, just because of the total of probability. OK, so usually in pseudo-randomness, what we are saying is that we have some random source, and what we want is that the output will be almost uniform. And usually people use the mean entropy definition in order to define random source, which means that the probability of each memory is at most 2 to the minus k. And the output should be almost uniform, and we use the notion of multiplicative error. And what do I mean by multiplicative error? Is that for essentially all hypotheses, a subset of hypotheses, their probability is at most L, some error, times their function. So L times age divided by the size of the hypothesis class. OK, so let's just summarize what I said so far. So a sampler with multiplicative factor L and mean entropy K and error A is one that if for every distribution P over the memories with large enough mean entropy, with mean entropy at least K, if for every subset age large enough, it holds that the following. So notice that the left-hand side is exactly the probability of age, and we want it to be small. OK. Usually, people in pseudo-randomness consider L to be equal to 1. They consider additive error. They add some error to it. And in this case, K must be large. But here's the cool thing about looking on multiplicative error. Now we can take k to be whatever we want. L is going to be larger, of course, but still, k can be anything. So if, for example, if we take k to be equal to zero, the smallest possible, which means that we can have some memory with probability 1, then L is going to be large, obviously, but still it can give us something. And what if we enlarge k by a bit? So let's, for example, consider a uniform distribution over a larger subset of memories. Then, naturally, L will decrease. And if we take k to be the largest possible, this will cause the distribution to be uniform over all the memories. Then in this case, L is going to be very small, 1. So we can play with what k is, and L will be affected, and we don't have to choose k to be large. But in general, P can be anything, right? So each memory state can have different values. So each memory state can have different entropy level. And by entropy level, I mean this expression, which is how much randomness there is in this memory state. So if we want to consider it as a mean entropy distribution, then we must take to be the minimum value. But if k is that small, we must take L to be very large. But what if there is a vertex with very small k, but all the rest are very high? One vertex, one memory with entropy level that is really small, but all the other have so much randomness in it. We want to lose all this randomness? So what we're suggesting is to squeeze the lemon some more and get from the vertices that have some randomness to get some more. So now I will present to you our new definition, the entropy sampler. And it says the following: that an entropy sampler with multiplicative error L as before and mean entropy k, and the new parameter is how much benefit we have. If for every distribution P and large enough set of hypotheses, the following holds. So what is this definition said? Is that if we have a memory M with high entropy level, then this term, the 2 to the power of b km, is going to be large. And still, even though it's large, still our error is small. So if we have a memory with a high entropy level, then this is going to be small as before, and we will have error L. But if we have also other memories with high entropy level, then this term can be large and basically say that we have less than error L. So this is our definition of entropy sampler, and I hope that it will be of independent interest. And thank you.